Section 1. The power of heat. An introduction to specific heat. Heat is everywhere. It warms our homes, cooks our food, and drives our weather patterns. Understanding how heat interacts with matter is crucial for comprehending our universe. One key concept in this realm is specific heat. Specific heat is a fundamental property of matter. It describes how much energy is required to raise the temperature of a substance. This seemingly simple concept has profound implications for our daily lives and scientific advancements. Imagine heating a pot of water on the stove. The amount of heat needed to bring the water to a boil is related to its specific heat. Different substances require different amounts of heat to change their temperature. From designing efficient engines to understanding climate change, specific heat plays a crucial role in countless applications. In the following sections, we'll delve deeper into this fascinating concept. Section 2. Defining specific heat. A measure of thermal inertia. Specific heat is defined as the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius, or 1 Kelvin. It's a measure of a substance's resistance to temperature change. Think of it as thermal inertia. Substances with high specific heat, like water, are like heavy shopping carts. They require a lot of energy, force, to get moving, change temperature. Conversely, substances with low specific heat, like metals, are like lightweight shopping carts. They require less energy to change their temperature. Water's high specific heat is why coastal areas experience milder temperature fluctuations than inland regions. The ocean acts as a giant heat sink, moderating temperatures. This property of water is also why it's an excellent coolant in car engines and power plants. Section 3. Unpacking the specific heat equation, Q=mc dt. To calculate specific heat, we use the following equation, Q=mc dt, where Q represents the amount of heat energy transferred in joules, M represents the mass of the substance in grams, C represents the specific heat of the substance in Jg/gC or JgK, and dt represents the change in temperature in dGc or K. This equation tells us that the amount of heat transferred is directly proportional to the mass of the substance, its specific heat, and the change in temperature. Understanding this relationship is key to solving problems involving heat transfer. Section 4. Unveiling the units, joules, grams, Celsius, and Kelvin. To work with the specific heat equation effectively, it's essential to understand the units involved. Joule. J. The standard unit of energy. 1 joule is the amount of energy required to apply a force of 1 Newton over a distance of 1 meter. Gram. G. The standard unit of mass. Celsius, dGc, and Kelvin, K, units for measuring temperature. The Celsius scale is based on the freezing and boiling points of water. The Kelvin scale is an absolute temperature scale, where 0 Kelvin represents absolute zero, the theoretical point at which all molecular motion ceases. When using the specific heat equation, ensure that all units are consistent. For example, if the mass is given in kilograms, convert it to grams before plugging it into the equation. Section 5. Putting theory into practice. Calculating specific heat. Let's apply the specific heat equation to a real-world example. Here's the problem. How much heat is required to raise the temperature of 50 grams of water from 20 degrees Celsius to 80 degrees Celsius? The specific heat of water is 4.18 joules per gram per degree Celsius. Now, let's solve this. First, identify the knowns. The mass, m, is 50 grams. The specific heat, C, is 4.18 joules per gram per degree Celsius. And the change in temperature, delta T, is 80 degrees Celsius minus 20 degrees Celsius, which equals 60 degrees Celsius. Next, plug the values into the equation. Q equals 50 grams times 4.18 joules per gram per degree. Celsius times 60 degrees Celsius. Finally, calculate the result. Q equals 12,540 joules. Therefore, 12,540 joules of heat are required to raise the temperature of 50 grams of water from 20 degrees Celsius to 80 degrees Celsius. Section 6. The significance of specific heat in our world. Specific heat plays a vital role in numerous aspects of our lives, from regulating our body temperature to influencing global climate patterns. Here are a few examples. In cooking, different cooking oils have different specific heats. This is why some oils heat up faster than others. In climate science, coastal regions experience milder temperatures than inland areas due to water's high specific heat. In engineering, engineers consider the specific heat of materials when designing engines, buildings, and other structures. In medicine, specific heat is used in medical treatments like hypothermia, where body tissues are heated to destroy cancerous cells. Understanding specific heat allows us to design more efficient systems, predict environmental changes, and develop innovative technologies. Section 7. Specific heat versus heat capacity. Understanding the difference. Specific heat is often confused with heat capacity, but they are distinct concepts. Specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius or Kelvin. Heat capacity, on the other hand, is the amount of heat required to raise the temperature of a given amount of a substance by 1 degree Celsius or Kelvin. Heat capacity depends on the mass of the substance, while specific heat is an intrinsic property independent of mass. Section 8. Factors influencing specific heat. Delving deeper. Several factors can influence a substance's specific heat. Substances with complex molecules tend to have higher specific heats. The specific heat of a substance can change depending on its phase, solid, liquid, or gas. Specific heat can also vary slightly with temperature. Understanding these factors is crucial for accurate calculations and predictions involving heat transfer. Imagine a graph showing the variation of specific heat with temperature for different substances. Section 9. Conclusion. Mastering specific heat for a brighter future. Specific heat is a fundamental concept in thermodynamics with far-reaching implications. From understanding everyday phenomena to advancing cutting-edge technologies, mastering specific heat empowers us to navigate and shape our world. By grasping the definitions, equations, and practical applications discussed in this essay, we can unlock a deeper understanding of the thermal properties of matter and their impact on our lives. As we continue to explore the universe and its intricate workings, specific heat will undoubtedly remain a cornerstone of scientific inquiry and technological innovation.